Isaac Newton was born in the year that Galileo died, 1642. I will not discuss his life sketch. What is only interesting is that during his student years, there was a plague in England, due to which his university closed down for a couple of years and he went home. Since he was a son of a peasant family, so he had to tend his farm, look after sheep during this time, and he proved to be useless as far as tending sheep is concerned. But in these 2 years of rustic solitude, he concentrated on a few problems, and in these 2 years he solved many of the problems that bugged that time. He, for example, invented differential and integral calculus. He solved the problem of gravity. He arrived at a law of gravity. He also arrived at the laws of motion, and he derived the trajectories of the planets starting from those premises, these postulates that he had made. And all that was done when he was just a young man, having to return to his home for a couple of years. When the plague subsided, he went back to his university, and somehow, even though his academic results were undistinguished, his professor understood the worth of this man, and so he recommended him to be given a professorship, the Lucasian professorship of the University of Cambridge, and then he became the Lucasian professor. Notice the time. It is important to understand the time. That was the time when slowly industries were being built. The feudal system was being replaced by the capitalist system. Industries were being built, and industries were producing goods that had to be transported. In order to produce goods, you needed a lot of fuel, you needed a lot of iron, and therefore mining had to be done. Importance of mining increased. And in those times, minings were rather primitive. Especially one major problem faced in the mine is to pump out the water and to ventilate the mines. So you needed better pumps for that purpose. When iron is extracted, then from the iron ore, iron had to be extracted, and that requires some idea of metallurgy, how to make good iron and stronger iron. The industrial requirement was that whatever was the produce of the industry have to be sold, and therefore that has to be carried over long distances. Now, the only way to carry things over long distances is not over land, because on land, in carts, how much can you carry? People realize that much more can be carried in waterborne transport. So, around that time, canals were dug for inland transport, and for sea transport, bigger and better ships had to be built. So, that posed a few scientific problems before the scientific community. For the canals, what should be the cross section of the canals, so that water can flow effortlessly? Will it be like this? Will it be like that? Will it be like that? So, various possibilities are there, and when you have some kind of a sluice gate, what should be the shape of the sluice gate, so that water can go through when it is opened. Regarding the seaborne transport, you have to make better ships, and ships in those times were made of wood, and later they started being made of iron. But when they were made of iron, they might sink unless they were made properly. Now, when a ship is buffeted by waves, that rocks, right? So, one has to figure out the laws governing the rocking of a floating body that concerned a problem of mechanics. The earlier problem of water flowing through various channels was a problem of hydrodynamics. In case of the seafaring, one major problem was how to figure out where you are in the middle of the sea. What is coordinate? How to figure that out? So long people did not know that, the ships had to go with the shoreline in view, so that they had to go very close to the shoreline. Naturally, they had to traverse longer distances. And around the 16th century, people had started going into the sea, leaving the shoreline. And then the problem was, how can you find the latitude and the longitude? Now, finding the latitude is relatively easier, because that depends on the season and the inclination of the sun. But finding the longitude is a more difficult problem, and for that one had to depend on your idea of the stars and the planets. So, the way to figure out the longitude in the daytime can in some ways be done by looking at the sun, but at night you have to look at the stars and the planets. So, people started looking at the stars and the planets and trying to find out the longitude from that. So, for the first time people started looking at that with interest, practical interest. And if when you started from a port, the Mars was at a certain point, when you were right in the middle of the sea 3 months later, then Mars would be at a different point. Then unless you know where it is in the sky, where it can be predicted to be in the sky, it's difficult to find your position using the position of the Mars. So, predicting the position of the planets became a practical necessity. You would notice that I am talking about certain necessities, certain demands coming from the society because of the societal changes that were happening, and the problems that Newton addressed were effectively these problems. The problems essentially concerned mechanics. Newton solved these problems, even though he did not directly talk about the practical problems. He abstracted the problems, theoretically solved those problems, which would have an immense impact on practical activities. But his discoveries had more impact than just that. Notice that in the first volume of his Principia Mathematica and the second volume, he was basically talking about the hydrodynamic problem of flow of water, problem of rocking ship and things like that. But in the last volume, he took up the problem which is presently known as the laws of mechanics and the laws of gravity, law of gravity. Law of gravity, any two bodies attract each other with a force equal to mass times g m1 m2 by r square. So, g times mass of the first body times mass of the second body divided by the distance between the two bodies square. That was the law of gravity. The laws of mechanics, the three laws you know, most important in this case was the second law, force is equal to mass into acceleration, and acceleration is a double derivative of position, and therefore that gives a differential equation. And if you solve the differential equation, you can write the differential equation for any body, you can solve the differential equations, and the solution will give you the ability to predict its position at a later time. And if you apply that technique to the heavenly bodies like the planets, you can predict the position of the these bodies at a later point of time, and you can wait and see whether it really goes there or not. People found that it really goes there, which means for the first time we acquired the ability of predicting heavenly bodies' motion. So far, people were only guessing, and all sorts of wild guesses were there regarding their positions, their motion, but now we have a law governed motion. We learned that their motions are not just arbitrary motions dictated by somebody, these are law governed, and we can know the law, we can predict their position. This had enormous impact on human psychology. Even his friend Edmund Halley, during his lifetime, he saw a planet, applied Newton's technique, Newton's method, and predicted that it will come back 74 years later. He died, but it came back 74 years later. So that gives people a lot of confidence in science. For the first time, people had a confidence in science, that science is true. It allows you to reach truth. It can predict behavior of bodies. So far we were thinking that these are heavenly bodies under the control of some extra supernatural force. So with that, so far the idea was that everything that happens because of what I mentioned as the final cause. Somebody makes that happen. For the first time, that idea was challenged. You have seen that Aristotle's idea was that force produces motion. And so whenever there is a motion, during the medieval period, people looked at who is now applying the force. And all the time, they came to an imaginary conclusion that some supernatural entity is applying the force to make any motion happen. So behind any motion, they saw a supernatural hand. But following Galileo, when Newton exactly formulated his first law, any body goes in a uniform rectilinear motion unless applied on by a force. From that, people understood that if you do not apply a force, force is not necessary for every motion. If you do not apply a force, things will go in a uniform rectilinear motion. So force or an entity, agent applying the force is not necessary for explaining every motion. But then we do see change in motion. The motion of Mars around the sun is change in motion at every point of time, because it is not going in a uniform rectilinear motion. Then also Newton showed that the agent applying the force is also a natural law. It is a law of gravitation. So it is a uniform law that applies to everything without exception. And so that also was no longer shrouded in mystery. So what applies the force, that was also known. And so slowly, after Newtonian mechanics came, slowly the earlier ideas of a divine hand in everything that happens, that receded. And because of that, again, materialism came to the forefront. Even though Newton himself may or may not have been a materialist, but what happened was, his mechanics again brought in materialism to the forefront, because no longer people saw a divine hand in everything that happens. But the materialism that was born through Newtonian theory, I mean, it was born actually following Newton, after Newton, but using Newtonian principles, that materialism was born with a defect. The defect was that the Newtonian picture gave people an impression of the universe where everything is law governed, everything moves, all the planets are moving in their own orbits, Whatever you do, you throw a cannonball, that also falls at a particular place. Everything happens following immutable laws. As if the whole thing is like a gigantic machine. The universe to the post-Newtonian scholars looked like a gigantic machine. And as any machine like a wristwatch is composed of smaller components, each put together makes the whole wristwatch. In the same way, whatever people looked at, they saw that as a component of a machine. And due to that reason, this kind of materialism, the materialism that was born following advent of Newtonian mechanics, is called mechanical materialism. So, let me delete this. What was born from the Newtonian mechanics was mechanical materialism. And people thought that they can predict everything. In fact, one Newtonian scholar, I mean post-Newtonian scholar, Laplace, whose Laplace transform you may have heard, Laplacian operator you have learnt of. So, that Laplace, he was basically a doyen of celestial mechanics. He wrote a book on celestial mechanics, and in that book he claimed that he can predict the motion of every particle if he is given the initial condition of every particle in the universe and a computing machine of enough capacity, then he will be able to predict the motion of every particle in future. And since we are all made of particles, he effectively said that the future of everything can be predicted using Newtonian laws, provided you are given enough computing power. Why can't we do that? We simply do not have that computing power, but in principle that can be computed. That was the point he was making. So, why is it computable? Because the whole thing is like a machine. So, this machine-like picture is a characteristic of mechanical materialism. There was another issue that was raised by almost contemporary people contemporary to Newton, is that okay, I understand that motion, once something has motion, it will continue to have motion. But then who imparted motion first? Who gave the first push? Who gave the first kick? That was the question that was raised. So, at faced that question, the Newtonian scholars fell back to idealism in some way, because they introduced the idea of there being some kind of a prime mover, a prime mover. Prime mover idea was essentially an agent that gave the universe the first push to start its motion, and after that you do not need his intervention, because everything would move according to the Newtonian laws. That was the idea. So, in this period we see the advent of Newtonian mechanics and the advent of mechanical materialism, and in the post-Newtonian period there were great developments in science, because materialism had come to the forefront. So, people were trying to formulate the understanding of everything in terms of material processes and phenomena, that enabled people to get rid of some of the unfounded ideas that were born in the earlier period. For example, people believed in spirits in many things, mysterious spirits. For example, magnetism was believed to be there was believed to be some spirit of magnetism. Whenever something burnt, there was a theory called phlogiston theory, the spirit of burning. People believed that the burnable substances contained a thing, a substance called phlogiston. And when a piece of wood, for example, burns, phlogiston comes out and forms a flame. That was the idea. From the hot substances to the cold substances, when heat flowed, there was heat transfer from a hot body to a cold body. People believed that the hot body contains a substance called caloric, from which the word calorie came. The caloric is a substance that flows from the hot body to a cold body. In the biological things, for example, the living matter, people believe that there is some kind of a spirit of biological matter called vital force. So, if the vital force is there, then the biological things will be there, otherwise the inanimate objects will not have vital force and things like that. So, there was this kind of subjective ideas prevailing in the scientific community, and in the period post Newton, people examined these. For example, Benjamin Thompson, who was later called Lord Rumford, he examined the process of whether the caloric was really there. When heat flows from a hot body to a cold body, then it was believed that the substance called caloric goes from a hot body to a cold body. So, he took some amount of, say, ice and allowed it to melt, which means that it has absorbed caloric, and then he weighed the ice as well as the resulting water, and he found that the weights are the same, masses are the same. So, even though it has melted, it has got more heat, but its weight has not changed. So, there is no physical material exchanged. Similarly, he did that for material things. He noticed that whenever a cannon is bored, that means the cannon, the cylinder of the cannon was bored, a lot of heat was produced. And he then tried to find out where is the heat coming from, and he measured the amount of heat by immersing the cannon in water and seeing how much the temperature of water increases, and he found out how much mechanical energy was spent in the act of boring, and he found that these are equal. Through these, he essentially established that the caloric was not a substance, it was basically a form of energy that was transferred. And you can transfer, you can convert mechanical energy into heat energy. Benjamin Franklin, he showed the things that were earlier believed to be the lightning, for example, earlier believed to be the wrath of God. Benjamin Franklin showed that it is nothing but flowing electricity. Earlier people knew about static electricity obtained by rubbing things, but now they realize that this is only static electricity, nothing mysterious about it. Galvani and Volta then invented ways of producing flowing electricity in batteries. So, Scheele, Priestley and Lavoisier, they almost at the same time produced oxygen, isolated oxygen, but because of their belief in the phlogiston theory, Scheele and Priestley could not identify that as a new element, which Lavoisier did. Lavoisier could figure out that this was a new element which is actually aiding burning and aiding breathing. So, he named it oxygen, and he invented or he introduced the method of writing the chemical symbols like CO2, the way we write. He introduced that way of writing chemical symbols. Thus, chemistry was born. It was no longer the earlier phase of alchemy. So, all these developments were happening in the time following the prescriptions of mechanical materialism. And then in England, the demand for increasing production resulted in people moving from wood as a source of heat to coal as a source of heat, and finally people analyzed the various ways of producing mechanical energy out of heat. And Newcomen, a person called Newcomen, he first invented a device to convert heat into the rotational motion of a shaft. It was slow, it was wasteful, but still it did its purpose, and it started being used in, for example, mines for ventilation purpose. But soon James Watt invented his steam engine, which revolutionized industry. Following that, most of the industries started using the motive power obtained from coal as the motive power for running the industries, and the industrial revolution started. So, with this I will close the class today, and the result of that we will take up in the next class. What was the philosophical impact of this?